Yeah, that's quite a huge title. I just I just blurted it down there. The subject is about image domain translation with generative adversarial networks. And the motivation for this is there are lots of simulations. Like I know of like 5 different simulations only for the SPL already. And the promise of generative adversarial networks is that they could make a translation from the images of simulation to the actual real world and basically improve all of them without any modification of the simulation themselves. And so I have some acknowledgements to make because I'm presenting my bachelor thesis about this, and I acquired a lot of data from the hoax, which was very nice. And I also used their version of the SimRobot simulator. For the same behaviors, which was quite nice too. So again, a big thanks to the hoax. And of course, the SimRobot was originally made and developed by BHuman. So that's also a big thanks to the BHuman team and that's for acknowledgements. So what did I do? Well, there's this reality gap between the simulation on the left and the real images on the right. And this is an image from the hoax data set from the RoboCup. And you can see they're not quite the same, not even close. And it means that if you train any machine learning algorithms on the simulation, you have to account for that difference. Otherwise, it will just not perform at all or just perform very poorly. And what I did in my thesis was try to make that translation possible with a GAN. And I'm just gonna show you. That took a few seconds to load, but like the image you could have seen in my abstract. On the left, there is a simulation, and on the right are all different generations of translations of that image to the domain of hoax data. So you can see there are all kinds of different lighting conditions, and you can see if you compare it back, it looks fairly a lot. It looks kind of like the actual real images. So I just wanted to start with that before going the theory behind it and how I made this. How did I do it? So let me start by introducing generative adversarial networks. They take a random noise vector and, well, let me first explain the generative. They try to take a random noise vector and generate some kind of image which is likely to come from some data set. And it's adversarial because there are actually 2 loss functions which compete with each other. So the generator tries to, what I just said, and the discriminator gets an image either generated or sampled from the real data set and tries to determine whether it's real or not. And the generator can use this information, the activations of the discriminator, to make adjustments and make the generated image more real. And well, it's slightly unstable because if the discriminator outpaces the generator by a lot, the slope is very poor because the generator is basically getting wrecked and it doesn't know how to fix it. But that's another topic. So that's the basis, but that's not quite what I used for my thesis, because I don't want random noise vectors here. I want a domain here. So this is image to image translation, which means that I have an image from domain A and try to generate an image from domain B, and maybe also the other way around. But we can't just use the original generative adversarial network for this, because what it will do if we do that, it will mode collapse, meaning that it will treat domain A just as another noise vector and just will randomly generate images which are likely to come from B, but it won't retain things like, it won't retain information, things like robots, balls, they might disappear. Like you may, if we apply this to the simulation, we may find ourselves on the other side of the field, and that's not desirable, especially if you want to use the annotations from the simulation, which is actually the whole point why you would want to use simulation. So there's some adjustments to make, and also some considerations. Because there are a bunch of image-to-image translations, and I first want to frame them in 3 different paradigms, so that you can at least understand some properties of the neural nets before I explain them in detail, which is unsupervised versus supervised, meaning that to solve previous mentioned problem about the mode collapse, you could just pair images from domain A and domain B and add an additional loss in the approximation of that domain B image, which is very labor intensive. But if you happen to have a paired data set, it's very nice. An example of this is sketches of shoes and actual shoes, and there has been research into making the transformation, and that works quite nicely. Unfortunately, I don't want to do this. I don't know if it's infeasible, but I really don't have the patience in aligning the simulation with real images, and it would be like a huge inconvenience. So I want a unsupervised method, one which doesn't rely on pairings. Then there's a second consideration, which is one-to-many versus one-to-one. One-to-many means that if I have one image from one domain, I can generate multiple images from the other domain, meaning that I have to do some type of disentangling, and that means separating the semantic space of an image with the stylized space of an image. And the semantic space means the actual information. So a semantic space is whether a robot is contained in that pixel, or the pixel is from from a robot, or from a field, or from a goal, or from some sort of background object. And stylized is the lighting, things like the lighting conditions, the color of the field, color settings of the camera, that kind of things. So back to the second point, because I tried both of them. So I tried 2 networks, one which does do one-to-many and one that does do one-to-one. And also the network which does one-to-many is disentangled or detangled. Another quick note before, before explaining architectures in detail, all of them use a variational autoencoder. And you can put this in this image, you can put this in the generator. So you have a domain A and you encode it to some latent space, and then you decode it, and then that's your generated image. So you have an image, you encode it latent space, and then you decode it to well, the original autoencoders are reconstructed images, but you can change the output image, of course. And the variation, so that was the autoencoder part. And the variational part is that instead of just some random numbers being represented here in the latent space, you use Gaussian parameters. So you have a bunch of means and variances from which you can sample at inference time. So during training time, you optimize those parameters of the Gaussian, and during inference time, you sample from them in order to generate variants in the reconstructed image. What this does is that this latent space will be regularized. Oops, okay. Meaning that if you have like representation of one thing and representation of another thing, so let's say a robot and a ball, you can interpolate them between those representations within that latent space. And that's simply very inconsistent in a normal autoencoder, and the variational one solves that problem partly because the variational autoencoders are notorious for being very vague. And that's where actually GANS come in. So without further ado, let's start with the first neural network I used to generate the images you saw previously. So this is CycleGan, and it basically doubles down quite literally. It's just adds another gun, meaning that instead of just one gun, you're trying to generate domain B from domain A. You add another one, which tries to generate domain A from domain B, and the cycle loss can be used to ground domain A in domain B, so that semantic information is preserved instead of forgotten. And I think, oh yeah, and the encoder and the decoder are variational autoencoders and are a variational autoencoder. So that's an important note, I think. And of course, the discriminator are still in play. So for example, if you have a cycle loss, you can go from A to B and then back to A, and you can still do a discriminator loss, determining whether it's still a realistic image of A. You may look at this later if things are still unclear. So I just explained the cycle loss. There's an additional loss in CycleGan, which is the identity loss, which is from domain A, you encode it, and then you immediately decode it again with this decoder. So you pretend as if these two spaces are the same, and that helps the grounding process and also helps with color transference, retention, actually, just that the color stays the same. Then we have a second approach, which is multimodal, unsupervised. What was it? Oh, yeah, multimodal, unsupervised image-to-image translation, Munit. And there are a number of things different. I'm going to two things actually. There's this shared latent space. So compared to CycleGan, where the latent spaces are separate, there's this shared latent space. So the variational autoencoders encode and decode to the same space. The assumption is that this space will be purely semantic, or it's supposed to be. So whatever the actual representation of a robot is, it gets represented in some abstract way in the shared latent space. And then depending on the domain, you can just decode it to that domain, and it will have this whole new outlook while the thing is still the same. Additionally, you have these style space for each domain, which is which is a result of this disentanglement, because you want to when you have this semantic representation, you might want to try different styles on top of it, so you can generate multiple images with the same semantic information but different style information. And these style domains are domain specific, so they're not encoded to a different domain. They're only in the same domain as they're singular domain. Yeah, they're singular domain. For my thesis, so that was the Munit, and for my thesis, I fiddled around with the loss functions. The loss functions from Munit are basically the same as the CycleGan. And what I did is I saw that features disappeared. I have some bonus images to show that maybe later. Like balls, they were disappearing, and parts of robots were also disappearing. So I tried to ground the translation more in the simulation. So the cycle loss is supposed to be bidirectional, meaning that you do A to B to A and a B to A to B. And what I adjusted was only doing the A to B to A in order to ground the semantic information in the simulator, which helped a bit. And I increased this loss to make it more relevant for the total loss function. So now that's what I did. And now how did it turn out? How good did I do? So there are two ways I used to evaluate my method, which was the Frechet inception distance. I will explain later. It's just a distance between images. And training an instance segmenter, because I really wanted to emphasize the potential of segmentation for this method instead of the boundary boxes, which has already been done I think in 2017 with a Unreal Engine simulator. So via Frechet inception distances is basically the curvature similarity over two data sets. So what you do is, well, that's just the Fréchet distance. And the inception part, the I, is a neural network, which is a classifier trained the inception net, which is trained for image classification. And what we use is the internal representation we use the feature vectors of this inception net in order to calculate distances between images. And this correlates a lot better with what humans perceive as the same image and different images compared to raw losses like just pixels, pixel differences. One of the most notable example is movement of objects, whereas if you do a pixel difference, the moved object will cause a huge disparity between two images. But for humans, it's still the same object, but just moved slightly. And that's not a big difference. So this kind of perceptual distance metric takes that into account. So these are the results. And so I tried CycleGan, Munit, and adjusted loss. And the adjusted loss for both of them, the simulation is just the original distance to the original simulation, which is not really that important, but it was interesting to see that it's interesting to see. And the real is the real data set, the distance from a translated data set to a real data set. And as you can see, the adjusted loss helps with that metric a lot. Second evaluation method was the MASK-RCNN, which is the instance segmenter. I quite naively used everything of the image. So I used an instance segmenter to segment both the field, lines, background, stuff which aren't actual instances. But it did quite well regardless. So I'm quite happy about that. I don't know if I have time to explain what MASK-RCNN does. Basically, it detects boundary boxes through previous works, and then tries to find a mask inside that boundary box of actually inside a ROI. And I think that's the gist of it. So here are some results. These are the effort precision scores. So it's the area behind the recall precision curve, below the recall precision curve. As you can see, lines are really bad, mainly because I used an instance segmenter instead of a semantic segmenter, but then I wouldn't be able to detect different robots. And I think that's a more important part of it. As you can see, if you train MASK-RCNN on pure simulation and then evaluate it on pure simulation, it will have the best results. I used these scores to measure the actual reality gap. So these top scores are internal. So we have a training set and a validation set of the pure simulation, or a data set translated with CycleGan, or a data set translated with Munit. So it's not really quite the reality gap, but below that, I used a small annotated data set of 500 images. I annotated myself and annotated the robots and balls, and calculated or evaluated the MASK-RCNN on those images. And there you will see that the multimodal network performs significantly better than the one-to-one translation, the not multimodal architecture. And that is one of the results of my paper. It's mainly because there's still some mode collapse in one-to-one translation, where images kind of get the same style. And of course, the data set exists out of many different games in different lighting conditions. So it won't prepare the segmenter trains for actual different lighting conditions. And by these metrics, I also could conclude that the reality gap in this case is about 15, or a little bit less than 15% for robots, and about 30% average precision % for balls. And here's a little preview of things I haven't run completely yet, which is supposedly much better, which is Panoptic segmentation, which does semantic and instant segmentation at the same time. But I don't have the results for that yet, so I couldn't present them. And I think that's it. Are there any questions? Whether to request a presentation file? I think I will submit my presentation, so that should be fine.
Yeah, well, we will collect all the presentations from the presenters who are fine with it, and we'll put it on the website so that you can look them up there afterwards.
But no questions? I don't know which network you're referring to, but GANS, so the network doing the translation, took about 24 hours to train on a GTX 2080 Ti. And the instant segmenter took about 12 hours. And for your information, the instant segmenter isn't actually usable on the robot. It was just to, it's way too large. It's just to present the potential of this translation.